Elementary Calc students, welcome to Chapter 5. In this chapter, the first thing we're going to start talking about is graphs and the derivative, and one of the challenging aspects to this conversation is making sure that you know what the graph you're looking at is depicting. Sometimes the graph that you see is going to be the graph of a function, other times the graph that you're looking at is going to be the graph of the derivative of the original function. So just something to keep an eye out for. Let's go in and see what the relationship is between these different graphs. The first aspect that we want to look at, especially when we're looking at the graphs of the derivative, is increasing and decreasing functions. I'm going to let you read this sort of sand-colored box on your own. This language is very mathematical. Everything that's in here is true. It's a description of the difference between increasing and decreasing functions on a particular interval. As you move from left to right on a graph, your x values are increasing. The question is, what are your y values doing? If your y values are getting larger, then your function is increasing on that interval. If your y values are getting smaller, then your function is decreasing on that interval. But it's always as your x values are moving from left to right, in other words, from smaller to larger. That could be from -17 up to -5. That's a movement from left to right. Those x values are going from smaller to larger. Or it could be from -2 up to +7, or +3 up to +12, but always moving from left to right with those x values, and then checking in on what the y values are doing. So that's what that sand-colored box there talks about. When a function is increasing or decreasing, you can talk about that as being the function's rate of change. Not specifically, not giving it a numerical value necessarily, but if your y values are increasing, then the slope at any given point on that interval is going to be positive because you're going uphill. And you can imagine drawing a tangent line that has a positive slope. It would go from low and left to high and right. Or if your function is decreasing, then a tangent at one of those points might be moving from high and left to low and right, going downhill from left to right. In this sand-colored box, I like this a little bit better because this is a description of increasing versus decreasing by looking at the first derivative. So this box says that if your first derivative is greater than 0, in other words, the slope of your tangent line is greater than 0, then your function is increasing. If it's less than 0, then it's decreasing, and if it's equal to 0, ooh, that sounded funny. If your first derivative is equal to 0, then your tangent line at that particular point is going to be horizontal. It's going to have a slope of 0. That could be on an entire interval. You could have a portion of your graph that's flat or horizontal, but often it happens when you're right at the top of a hill or at the bottom of a valley. Those are some typical points where your first derivative is equal to 0. We'll see some of those. But first, I want to look at this example with you because this is exactly what I was talking about. This problem, this example, is telling us that the graph that we're looking at here is not the graph of f of x, it's the graph of f prime of x. And the question is, we're being asked to find the open intervals where our function is increasing, and then where is it decreasing. Again, I have to say it one more time. This is the graph of f prime of x. It's our derivative. So let me ask you this. When x is equal to -1, what is f prime of x? We go to our x value of -1, we come up here and have a look, and it looks like f prime of x is equal to +3. In other words, the slope of the tangent line is positive. If you have a graph where your tangent line has a positive slope, for example, Let's draw maybe something like this. At this point right here, the slope of my tangent line is positive because it's going from low and left to high and right, or rise over run is taking us in the positive direction. So taking that idea and applying it here, it looks like since my first derivative here is positive, my original function f of x would be increasing there. When x equals maybe negative 1.7, the y value, f prime of x in this case, is still positive. So the slope of the tangent line to the original function, where x equals negative 1.7, would also be positive. Coming back over here, where I have this positive sloping tangent line, wouldn't you say that our function is increasing? Doesn't it look like it's going, what is happening? There we go. Doesn't it look like my function's going uphill here to you? As I go from left to right, my y values are increasing. So again, a positive sloping tangent line tells me that my original function is increasing. A negative sloping tangent line, let's try one of those on this same graph over here to the top right. That's not really a tangent line. Let's get in here, maybe just a little one. This tangent line has a negative slope. And I think it's safe to say also here that our function is going downhill as we go from left to right. Our y values are getting lower. Therefore, we would say that our function is decreasing there. So all of this is just to attempt, although it doesn't feel like it's going super well, to attempt to illustrate this idea for you, that a positive sloping tangent line tells us that our function is increasing, a negative sloping one tells us that it's decreasing, and if we look at the part of this curve right here, the tangent line at that point, at this point right here, I think would be horizontal. So our function is neither increasing nor decreasing at that point. It's like a little flat spot right at the bottom of the valley. Take a rest there before you start marching uphill. All right, so back to this graph that was given to us. We saw a number of points on this graph where the y value, the f prime of x value, is positive, which means that our function is increasing. All of these points tell us that f prime of x is positive, and therefore our original function is increasing on the interval from -2 to +2. I'm going to come up here under my instructions. I'm going to write it down here. It's increasing from -2 to +2. You're going to have to write that down somewhere else unless you've printed these notes. Increasing, maybe increasing, and then put a little colon, and then you could put -2 to +2. Our original function is decreasing where f prime is less than 0, and this is where f prime is less than 0. This is also where f prime is less than 0. It's below the x-axis there. And I would be willing to bet that this goes all the way down and all the way left, all the way down and all the way right. So I'm going to say that my function is decreasing on the intervals, plural, from -∞ up to -2. And maybe we'd separate those by a comma, potentially a union sign, but I'm going to go with a comma for the moment, and then starting again from +2 going up to ∞. On those two intervals, our function is decreasing because the first derivative on those intervals is negative. I should mention, as long as we're here, these are the points, these x-intercepts, these are the points where our function is neither increasing nor decreasing. Those are the places where f prime of x is equal to 0. So we're probably at either a high spot or a low spot on our graph, where x equals -2 and where x equals +2. So speaking of f prime equaling 0, the derivative can change signs from positive to negative. Obviously, that's happening in this graph up here. F prime is negative here, and then here f prime is positive. So it changed when x equaled -2. Here f prime was positive, and here f prime is negative. It changed when x was equal to +2. So the derivative can change signs from positive to negative or negative to positive, and that happens at points where f prime of x is equal to 0, and sometimes where your first derivative does not exist. Maybe there's an asymptote there. And the values of x where that happens, those values are called critical numbers. So in the previous example that we saw, the critical numbers were -2, x equals -2, and x equals +2. So in this gray box, this is well articulated. Critical numbers of a function are the numbers in the domain of your original function for which f prime is equal to 0 or f prime does not exist. So you're either at the top of a hill, because here the slope of the tangent line is 0, or you could be at the bottom of a valley, this point right here, slope of the tangent line is 0, or perhaps you're working with a function that has an asymptote, maybe at +2. So we would say that x equals +2 is a critical number because that is a point, or x equals 2 is a value for which the first derivative does not exist. So the critical numbers are the x values. A critical point is an xy ordered pair. You normally think of a point as x comma y. So that'll help you remember that, hopefully. A critical point is the actual x comma y. A critical number is just the x coordinate. Now, if you have a vertical asymptote, you're not going to have a critical point there because there is no point. The function is undefined. You will, however, have a critical value there. My little example here, when x equals +2, x equals 2 is a critical value, but there's no critical point. It's an asymptote. And this problem is asking us to find all of the critical numbers. How are we supposed to do that? Right. It's so difficult to point because this image is mirrored right there. The f prime of c equals 0. We need to take the first derivative of our function and set it equal to 0 in order to find the critical numbers. You're putting that in your notes. You're putting a star next to it. You're highlighting it. How to find critical numbers. Take the first derivative, set it equal to 0. Okay, let's do that. F prime of x is equal to, I'm taking the exponent, multiplying it by the coefficient. 3 times 2/3 is just 2. Keep the variable, decrease the exponent by 1, plus, take the next exponent, multiply it by the coefficient. 2 times 3/2 makes +3. Keep the variable, decrease the exponent by 1, so it becomes a 1, minus, derivative of 27x is just 27. Derivative of the +2, our constant value goes to 0. Great, so this is our first derivative. Now we need to set this equal to 0. And then we have to solve this. Let's see, 27 is made of all 3's, and the 2 is made of just a 2. So if I borrow a 3 from the 27, it turns into a 9. And if I give the 3 to the 2, it changes the 2 into a 6. And 2 and 6, or sorry, 3 and 9, I'm losing it. 6 and 9 are 3 units apart. 3 units apart. What I'm doing is I'm doing some of the parts of the process of the AC method. I'm doing them, well, in my head, but I'm saying them out loud for you, just so that you can get a little insight on how I'm deciding to proceed. And since I just determined that 6 and 9 are 3 units apart, I think I'm going to be able to factor this. So I'm going to try to factor this using the AC method. Remember that this is ax squared plus bx plus c. So those are my 3 values. A times c is equal to 2 times negative 27, which is equal to negative 54. I'll take the negative 54 and make my list of factor pairs of numbers that multiply to negative 54. So that's 1 and 54, 2 and 27, 3 and 18, 4 is not going to work, 5 is not going to work, 6 is going to work though. 6 goes into 54 9 times, and I found it. Now, these numbers don't multiply to negative 54. What I need to do is make either the top number positive and the bottom one negative, or the top one negative and the bottom one positive, and they need to add together to equal my b value, which is positive 3. So I'm going to choose a positive 9 and a negative 6. I'll use those to split my middle term. So I'm rewriting my equation 0 equals 2x squared minus 6x plus 9x, combined like terms, that equals positive 3x. That's our b value, minus 27. And then we will factor by grouping. We'll factor these 2 terms, factor these 2 terms. So now I have 0 equals, the common factor in my first group is a 2x, leaving me with an x minus 3. Common factor in my second group is a positive 9, leaving me with an x minus 3. I'll factor one more time. 0 equals, the common factor is the x minus 3. The leftovers, as I like to call them, are a factor of 2x and a factor of positive 9, so those turn into 2 terms. And now we can use the zero product property and set each one of these factors equal to 0 and solve. So x minus 3 equals 0, 2x plus 9 equals 0, x equals positive 3, and x equals negative 9 halves. These, ladies and gentlemen, are our critical numbers. More than anything, that was a review of the factoring process than taking a derivative, but that's why we have to have solid algebra skills in order to be successful as we keep marching through our math classes. Still have to know how to factor. All right, and there's a test for increasing and decreasing. So we're going to go through some motions to determine specific intervals where our function is increasing and decreasing. So let's have a look at that next. So this process tells us that we need to locate the critical numbers, which we just finished practicing, and then I'm going to take them and put them on a number line in order to chop the number line up into a series of intervals. And then we're going to test x values from those intervals in our first derivative and see if the first derivative returns positive or negative values. And that will tell us whether our function is increasing or decreasing on those respective intervals. Let's try it. So find the open intervals where the function is increasing and where it is decreasing. So the first thing we're actually going to do is find out where it's neither increasing nor decreasing. We're going to find out where f prime is equal to 0. So let's find our first derivative. F prime of x equals, oh, now this is a little tricky because it's a fraction. So you could either use the quotient rule or I think what I'll do is I'm going to erase this prime in here, and I'm going to rewrite my original function as x squared plus 1 to the negative first power. That way I can use the chain rule in order to find the derivative. Okay, so let's do that now. So f prime of x is equal to, take the exponent, multiply it out front, so there's a negative 1, times the existing inner function, x squared plus 1, decrease the exponent by 1, so now it's a negative 2, and then multiply by the derivative of the inner function. The derivative of x squared plus 1 is 2x. And then let's just clean this up a little bit. It's going to be negative. There's a factor of 2 in the numerator, a factor of x in the numerator, and the x squared plus 1 goes in the denominator and is now squared because we have x squared plus 1 to the negative second power. All right, so that's our first derivative. Now we're going to take that first derivative and we're going to set it equal to 0. That is negative 2x over x squared plus 1 squared. How do you make a fraction equal to 0? Can you give me an example of a fraction that's equal to 0? 3 over 5, does that equal 0? Negative 2 over 7, does that equal 0? What about negative 2 over 0? Does that equal 0? It does not. Division by 0 gives a result of undefined, or positive or negative infinity. For a fraction to be equal to 0, we need the numerator to equal 0. So in order to make this happen, we need 0 to equal negative 2x, or I should say that from right to left. We need negative 2x, the numerator, to equal 0. How do we make that happen? X needs to equal 0. This is our critical number, and in your notes you should label it critical number. Sometimes there's more than one critical number. In this case, there happens to only be one. The other thing that we should check to see, so this x value makes f prime of x equals 0. You should look at your first derivative and see if there's any way to make your first derivative undefined. There are not any x values that cause division by 0. So we don't have to worry about f prime equaling undefined or being undefined, and thus causing a critical number to occur at maybe a vertical asymptote. So our only critical number now for sure is that x value of 0. So I'm going to take my number line, I'm going to put 0 here, and then we're going to test and test. We're testing the two intervals created by that critical number. And maybe we'll test x equals negative 1 and x equals positive 1. You can choose any x values you want to in those intervals in order to test to see whether your function is increasing or decreasing. F prime of negative 1 equals negative 2 times negative 1 over negative 1 squared plus 1 squared equals, that's a 2 in the numerator, and negative 1 squared is positive 1, plus 1 makes 2, squared makes 4, which is greater than 0, therefore increasing on that entire interval that's to the left of 0. So from negative infinity up to 0. And it's an open interval. So we need to use parentheses on both ends of that. And then let's test f prime of positive 1. Negative 2 times positive 1 over 1 squared plus 1 squared equals negative 2 this time over 4, which is less than 0, therefore decreasing. On the interval that is to the right of 0, so going from 0 all the way up to positive infinity. And those are the two components of your final answer. What is it that's increasing or decreasing on those two intervals? Your original function. How did we determine that? We looked at what the first derivatives are doing. Everywhere to the left of 0, the first derivative seems like it's going to be negative. And, everywhere to the left of 0, our first derivative is going to be positive, therefore our function is increasing. Everywhere to the right of 0, our first derivative looks like it's going to be less than 0 or negative, therefore our function will be decreasing to the right of 0. And an applied problem for us to check out, a profit analysis application. We have a manufacturer selling telephones with this cost function, and it looks like our x values are between 0 and 800. We're also being given a revenue function for those same group of, or that same group of x values, and we want to determine the interval or intervals on which the profit function is increasing. Okay, that means we want the first derivative of our profit function to be greater than 0. That's a skill that if you haven't finished developing it yet, you need to develop it. You need to get to the point where you can read profit function is increasing, and to you that needs to say the first derivative of the profit function needs to be greater than 0. So we need to figure out the first derivative of the profit function. No big deal. Except we weren't given a profit function. So we need to develop a profit function. P of x is equal to, profit is equal to revenue minus cost. I almost wrote the word cost. C of x, there we go. And that's equal to 9.2x minus 0.002x squared minus our cost function, which I'm going to put in parentheses, 6.68 minus 0.0002 x squared, close. Let's distribute that minus sign before we go any further. 9.2x minus 0.002x squared minus 6.68 plus 0.0002x squared. Okay, there we go. So I distributed dist, and then we will CLT, combine like terms. What do we have for x squareds? I've got a negative 0.002 and a positive 0.0002. Dare I do that arithmetic in my head? I'm going with that. And then I'm double checking because I stink at arithmetic. More complicated stuff I can do, but adding and subtracting numbers in my head is just, it's not my strong suit. I can't be good at everything. I'd like to be good at everything, but I'm just not. Negative 0.002. I guess it's good that I know my strengths and my weaknesses. That's important. And it just so happens that I was able to do that arithmetic in my head. Okay. Any x values? Oh, we do have this one term. Oh, I left an x out, didn't I? Did you see that? Why didn't you say something? I left an x out. It's supposed to be 6.68 8x. Let's get those x's in there. X in there, x in there, good. Okay, so now we're combining like terms, and I've got 9.2 minus 6.68, and that is equal to 2.52. Make sure my decimal point shows up there with an x after it. Okay, so this is our profit function. Yep, that looks good. Okay, now let's find the first derivative of the profit function. Now notice this profit function is a second degree polynomial because it has an x squared and the next to the first power, and that's it. So it's a second degree polynomial with a leading coefficient that's negative, which means that if we graph this, it's going to look like an upside down parabola. And we're trying to figure out the intervals on which the profit function is increasing, which means we're going to be looking at this part of our graph, everywhere from the vertex and to the left. So our answer is going to be, well, I don't know exactly what the answer is going to be. It'll be interesting. Let's see. First derivative, p prime of x is equal to negative 0.0036 x to the first power plus 2.52, and then we're going to set that equal to 0. So we need to subtract 2.52 from both sides. And then we need to divide both sides by negative 0.0036. Dividing by negative 0.0036 equals 700. That turned out a lot nicer than I thought it was going to, I'll be honest. So x equals 700 is the point where our profit function is neither increasing nor decreasing. You might want to include that in your notes, because when x equals 700, our first derivative is equal to 0. That tells us that our profit is neither increasing nor decreasing. The 0 is what tells us that. And when is it happening? When x equals 700. What's happening to the left or to the right of 700? If you go back to looking at our parabola, if this is the only point, we know that it's an upside down parabola, the original graph of our profit function. This must be the point where x equals 700. And we're only working on the interval. If you look at the original problem toward the top of the screen, a little bit right of center, we're only looking at this interval where our x values are between 0 and 800. And if you look back at this little graph that I drew, this is certainly the side of the parabola where it's increasing. As we're going from left to right, it's going uphill. So I feel confident in saying immediately that the interval on which the profit function is increasing is from 0 to 700. Could we take the 700 and put it on a number line and test over here and test over here? Maybe we take 600 and put it into the first derivative, and we take 750 and put it into the first derivative, a number that's to the left of 700 and a number that's to the right of 700. Absolutely. But I'm telling you, to the right of 700, plug in a 750 into the first derivative. It's going to come out negative. Plug in 650, maybe, into the first derivative. It's going to come out positive. P prime of, let's use 650, is equal to, I'm not going to do all of the arithmetic. What I'm going to do is, if you're using a graphing calculator, let's see if I can do this. My recommendation is to, it's tough to get this in focus. I would type in your first derivative equation with x's. Okay, so I would go ahead and right on the home screen on your grapher, I would type in negative 0.0036x plus 2.52. Yeah. Why isn't that working? Because I'm hitting the wrong button. Plus 2.52. Enter. Okay, so now I've got that typed in. You can't see it, but I did type it in. Yeah, maybe if you zoomed in, you could see it there. But it gave me some weird number as an output value. So now what I'm going to do is I'm going to take 650. I'm going to type in 650 on the home screen, 650. And then down here in the bottom left corner, there's a button that says STO. That's for store. And I'm going to store the value of 650 in my x variable. So I'm going to hit the button that I normally use for all of my variables. It has an x and a t and a theta and an n. So I'm going to store it in x, and then I'm going to hit enter in the bottom right, and it just shows me 650 still. And then I'm going to hit, where am I? And then I'm going to hit second enter. Well, I ended up typing that in twice, I guess, but I hit second enter a couple of times until I'm showing that negative 0.0036x plus 2.52 expression again. And I'm going to hit enter. And now it's telling me an answer of 0.18. So what it did is it took the x value that I stored, which was 650, and it processed that equation with that x value, and it gave me out a positive 0.18. So I can come in here and write down 0.18, which is greater than 0, therefore increasing on 0 up to 700. The 650 that I typed in was just a representative of that interval. So you want to make sure that you're still writing increasing from 0 to 700, not just up to 650. And then let's also process our first derivative for an x value of 750. So I'm going back into my calculator. I type 750 and then the store button, STO, in the bottom left-hand corner. And then I'll hit my variable x near the top left under the mode button. Enter, and I see the 750 on the right-hand side. And now I hit the second button, which is in the top left corner. So right up here where my thumb is. Second, enter in the bottom right, and then second enter again. Now I see my equation there with the 0.003x plus 2.52. I hit enter, and I get negative 0.18. So let's write that into our notes also. P prime of 750 is equal to negative 0.18, which is less than 0, therefore decreasing on 700 up to 800. This is the only one that I'm interested in because the question asked me on what interval is my function, profit function, increasing. The answer is going to be from 0 to 700. But just to illustrate, I threw in the 750 to test the other side of 700. But I think it would be ideal, the teacher in me would love it, if you recognized that the graph is going to look something like this. That's the approximate shape of the graph of your original profit function. That was supposed to be an arrow. That's enough like an arrow. And if you use that knowledge that you have of algebra, you can save yourself a little bit of time. Now, if you're taking a test or you're doing an assignment where you have to show all of your work, maybe showing the graph and writing a little commentary about the shape of the original profit function and then using that in order to make the decision about only testing to the left of 700, maybe to confirm that it's going to be increasing. But you heard me say it before I did any of the arithmetic. I knew that it was going to be from 0 to 700, and you can know that too, because I know you've got algebra skills. You made it this far in your study of math, so don't hesitate to utilize that knowledge that you have, and I'm pretty sure that is where these notes end. So I thank you for joining me for this first section in a new chapter, and I'm going to head on over to the next one. See you there.